China engineered its high-speed rail network to support trains traveling at a blistering 600 kilometers per hour. But during early test runs, the ambition collided with a terrifying structural reality. As a train crossed this massive suspended span, the bridge began to dangerously wobble at only 100 kilometers per hour. A massive investigation followed, working backward from the bridge deck down to the soil. The structural design was flawless, and the math was perfect. This was a crisis of material integrity, specifically a failure of consistency in the concrete foundation. The probe discovered that the foundations and sleepers had been cast using raw industrial waste, unprocessed fly ash sourced directly from power plants. Without chemical validation, the material varied wildly in every batch, a choice that investigators eventually categorized as criminal negligence. In a state-driven megaproject, that level of negligence carries total personal liability. The investigation concluded that the chief engineer was solely responsible for the structural compromise, leading to the most extreme consequence, a sentence of state execution. Treating foundational concrete chemistry as a shortcut for cost-cutting creates more than an engineering error. It establishes an unforgivable legal and financial liability. This chart illustrates the risk of unvalidated materials through the compressive strength of concrete. At 7 days, the blocks show excellent strength, easily passing early inspections. But by the 28-day mark, there is a steep drop-off, a structural collapse known as the haphazard phenomenon. This happens because raw fly ash is highly irregular in size and shape. To make the concrete workable, contractors end up pumping excessive amounts of water into the initial mix. As the cement cures, it triggers an intense exothermic reaction. The internal temperature of the mix rises so sharply it can physically burn a worker's skin, and deep inside the foundation, that heat causes the trapped water molecules to boil. That boiling water turns into vapor, forcing its way to the surface and violently tearing through the curing concrete. It leaves behind a permanent network of microscopic structural fissures. Stranded inside those new cracks is a corrosive byproduct, unreacted free lime. These unstable pockets stay trapped within the structure, degrading the concrete from the inside out over time. ISI-marked processed fly ash acts as a precision-engineered countermeasure. It contains active silica designed to seek out and chemically bind with those volatile lime deposits. The processed ash consumes the free lime, converting it into an additional cementitious bonding agent. This process cools the reaction and prevents microcracks from forming, resulting in a dense, monolithic structure. The total lifespan of a multi-million-dollar structure is ultimately decided by the invisible, microscopic chemical consistency of its ingredients. For decades, the National Highways Authority of India maintained a complete ban on fly ash because of these unpredictable failure rates. That standard was finally challenged and updated during the construction of the Mumbai-Pune Expressway. Developers proved that by using chemically validated processed fly ash, they could strictly control the heat of hydration and pour kilometers of crack-free, high-performance concrete. A different contractor working on a connecting stretch of the same highway reverted to using raw, unprocessed ash to save on upfront costs. Today, that unprocessed section remains a compromised surface. It is riddled with surface cracks that require a continuous, expensive cycle of patch repairs to handle the vehicle loads. The minor savings gained from unvalidated materials are quickly eradicated by the long-term financial drain of structural remediation. These exact same principles of chemical validation apply to foundational earthworks, where material requirements scale up by orders of magnitude. Engineers at the Ambi Valley project in Lonavala faced a major geotechnical hurdle when the native soil failed to meet the necessary load-bearing capacity for the road. They utilized a specialized P40 processed fly ash blend to chemically stabilize the earth, successfully altering the soil's chemistry to support the massive development. This stabilization technique provides the roadmap for laying massive foundational assets, such as 300-kilometer earthen embankments for heavy infrastructure. This high-volume capability provides the stable foundation required for visionary international projects, like the upcoming Galefu Organic City located in the mountains of Bhutan. Adopting processed fly ash over unpredictable raw materials provides the uncompromising engineering standard required to build a safe and enduring structural future.